So we're going to start off by looking at section 7.5, which is kind of continuing with identities. We left off with some basic ones last time. I think we did Pythagorean, reciprocal, and the tangent and cotangent. So here's a few more we're going to look at. There's 4 sum and difference identities that are the most important. There's adding with sine and cosine, so there's 2. And then subtracting with sine and cosine, so 2 more. There are ones for tangent, but you can always get around using tangent if you know the sine and cosine ones. It's faster if you know the tangent, but if you're just trying to remember a lot of stuff and you can only remember certain ones, the sine and cosine will work for everything. Alright, so let's look at the difference between those 2 things. The sine of x plus 3 in parentheses, and then the sine of x with a plus sine of 3 kind of separated out. So first, I just want to see if we think these are the same. And the way we can kind of figure it out without even graphing and without even plugging anything in is when you have a plus 3 inside parentheses, what does it do when you add or subtract a number inside parentheses in terms of like shifting it? What does a plus 3 do? About Kaya?
It moves it.
When it's inside, it's not vertical. That's when it's on the outside. So it moves it to the left or to the right. And which one is it in this case? Let's see. Plus, yes, is going to go to the left. So the first one is a shift 3 units left. Now, the other one, you're doing plus, and it's not even plus 3. It's plus sine of 3. All right. So this is a vertical shift, right? And it's not even 3 units. So vertical shift, horizontal shift, those 2 things aren't the same. All right. So if you want to deal with a sum, you can't think of like distributing the sign. That does not work at all. All right. There is something that works, and we'll take a look at what it is. Another way you could verify that they're different is graphing. They won't look the same at all. All right, so I told you there's 4 basic ones we're gonna look at. We are gonna do the tangent, but again, sine and cosine are the most important. And we're gonna start out with the cosine difference formula. So what the cosine difference formula gives you is a way to deal with cosine when you're subtracting 2 things inside parentheses. And you might be wondering, why would you ever subtract 2 things? Why wouldn't you, like if it was 40 minus 10, why wouldn't you just do 40 minus 10 and just say, okay, it's 30? I'm going to show you why you would have a difference inside in a minute. Okay, and all 4 of these formulas, they look pretty similar. So this one is if you want to do the cosine of a difference, I'm going to call alpha the first and beta the second, because alpha comes first and beta comes second. It's the cosine of the first, cosine of the second, plus sine of the first, sine of the second. Now there's a proof of that formula, but I don't want to get too involved with the proof because it does take probably about 10-15 minutes to go through it. And for the purposes of what we're doing, which is just kind of using the formulas rather than proving where they come from, it really would take a big chunk out of the class. So we're going to hold off on proving it. What we will do is use this formula to prove other ones. That's very easy. Bless you. Right? But the proof, it involves basically drawing a triangle inside of a circle and then kind of rotating that triangle a little bit and looking at a couple different angles. So it's doable, but it would just take about 15 minutes. So we'll just write down the formula. Does anybody have that formula? So cosine of the first, cosine of the second, plus sine of the first, sine of the second. So what I want to do is find the exact value of the cosine of 15 degrees. Now, if I try to do it I don't even need to type it in because you know what'll happen. If I type it in on the calculator, it's going to give me a decimal. Okay, I'm not looking for a decimal. I'm looking for the exact answer. What angles do we know how to work with now and we can find exact answers? There's certain angles that we work with a lot, especially when we do like the unit circle. Anyone remember? Yeah?
30, 60, 90, 45.
Okay, so she said 30, 60, 90, 45. Okay, so those are some of them. Can anybody generalize that? Because there's more too.
Multiples of 15.
Any angles that are, well, we don't know how to do the multiples of 15 yet, but you will. Right now, we know how to do multiples of, yep, 30. So 30, 60, 90, 120, and include some of the stuff that she just said. And what else? Multiples of, what other special right triangles do we use besides the 30, 60, 90?
45.
The 45. So right now, we know how to do unit circle trig with any angle that's a multiple of 30 or 45, I hope. So once we know how to do that, then we can extend it to the 15s, right? The only thing we have to do is somehow rewrite the number 15. We have to write it using angles we already know how to work with, 30s and 45s. Okay. Now we only know one formula right now. We only know the cosine difference. Anybody think they can tell me how to rewrite 15? It has to be a difference. Okay. But it can't be like 20 minus 5. It's got to be angles that are multiples of 30 and 45. Yeah?
30 and 45, so just like 45 minus 30.
Sure. We can do 45 minus 30. Now what we're going to do is we're going to go back to that formula. We're going to fill in 45 for alpha and 30 for beta. Okay. And all the answers here are going to involve like square root of 3 over 2, square root of 2 over 2, things like that. All right. So we're going to see the decimal like 0.866, that's square root 3 over 2, and 0.707, that's square root 2 over 2. It's going to come up a lot. But if you know the two things I just said, you really don't have to go through and do all the unit circle stuff. Just kind of know those decimals and what they're equal to. All right, so let's look at our formula. Cosine, cosine, plus sine, sine. All right, so we're going to have cosine, cosine, plus sine, sine. And now fill in first, second, first, second. So 45, 30, 45, 30. 45, 30, 45, 30. If you do that calculation out, it will give you the cosine of 15 degrees as an exact answer. So we'll do it, we'll get it, and then we'll check and see if the decimal, when we type in cosine 15, matches what we get here. Alright, so let's start with cosine 45. If you don't have it memorized what it is, okay, you don't want to go through the whole unit circle, that's fine. But you have to recognize the decimal that you're about to get. The cosine of 45 is 0.707. What is 0.707 as a fraction with a square root? Well, 45, that 45 degree angle involves the 45, 45, 90. So we just have to remember how long are the sides in a 45, 45, 90 when it's in a unit circle. They involve the square root of what number? Yeah, involve the square root of 2. So somehow 0.707 has something to do with the square root of 2. It's not just the square root of 2, because the square root of 2 is 1.4. Anyone have a guess how you could get 0.707 with the square root of 2? Yeah?
Divided by 2.
Right. .707 is the square root of 2. 2 divided by 2. Okay, you just have to memorize that cosine of 45 is root 2 over 2. Right? Or recognize the decimal. Okay, either way. So that one is root 2 over 2. Times, right? Now let's do cosine 30. Again, either memorize the cosine of 30 or recognize that decimal as something. 0.866. Okay, this is in the 30, 60, 90 triangle. So what square root was involved in this one? Square root of 2 over 2, that was the 45, 45, 90. 30, 60, 90 involves the square root of what number? Yeah. Not in the unit circle. I mean, maybe you could come up with a different version of the triangle, but in the unit circle one, it's not the square root of 5. So, Joe, do you have a guess? So when we have the unit circle, think back to labeling your triangle. There's the short side and the long side. Hypotenuse is always 1. The short side is a half, I'll tell you that, which doesn't help you at all. And then the long side is what I'm looking for. Yep. Chris?
I thought you were asking for the angle of the triangle.
No, not the angle. We've got the angle. We got to figure out what the cosine of that angle is. I mean, it's 0.866, but we got to write it as an exact answer. Want to remember that? Yeah?
Square root of 3.
Yep. It involves the square root of 3. So what can you do with the square root of 3 to get 0.866? Because the square root of 3 is about 1.7, so it's not just the square root of 3. It's kind of like what we did last time.
Divided by 2.
Yeah, the square root of 3 over 2 is 0.866. All right. So the cosine of 30 is the square root of 3 over 2. Right. Now let's do the sine of 45. Okay. Again, if you know what it is, that's good. If you don't, then you got to recognize it from that decimal. What's the square root of 45? Oh, just it's not a new number. It's one we already did earlier. It's one we've already done. Not sure. Yeah. It's the square root of 2 over 2. All right. So sine of 45 and cosine of 45, those are the same answer. And then the sine of 30. So sine would be opposite, if your angle was right there, over hypotenuse. How long in a 30, 60, 90 is the question mark side? I told you that one earlier, and I said it doesn't help. Because it didn't help for this, but it does help for the other, for what we're trying to do now. Yep, it's 1/2. Okay, so sine of 30, opposite over hypotenuse, that's opposite, that's adjacent, and the hypotenuse is 1. So just keep that triangle in mind if you ever get stuck on the 30, 60, 90, and you can always use it to figure out the numbers you're looking for. Okay, so now let's multiply together what we have. Tori, what do I get if I multiply these two fractions together on the left? Which is, you can combine that. Square root of 6 over 4, right? When you're multiplying fractions, remember that denominator changes. It's not a common denominator, right? This one happens to have common, but you just multiply them together, and whatever you get is what you get. Gabe, how about my second fraction?
It'll be square root of 2 over 4.
Yep, square root of 2 over 4. And now, since they do have a common denominator, we can just put them all together and write the final answer. So Emily, how could I put those together and get my final answer? Yep. Can't combine those square roots because they're addition, but you can just put them over the same denominator, and that is the exact answer for the square root of 15. Okay. And that's easy to check. Let's take the cosine of 15. Should come out to 0.9659. Let's take that in and see what we get. Square root of 6 plus square root of 2. Since I didn't put parentheses, I'm just going to type the top in first and then hit divide by 4. 0.9659, 0.9659. Exactly the same there. Okay. Any questions on that? Right, so now we know how to find, at least for cosine, we know how to find our first one that's a multiple of 15. So by the end of today, you should be able to find all the exact answers for any multiple of 15. So that automatically includes the 30s and the 45s, and then like the 15 and the 75 in each quadrant. We couldn't do those before, okay, but now we can. Okay, I want to verify that this identity is true. It says the cosine of pi over 2 minus theta is the same as the sine of theta. Let me graph it just to kind of show you visually what we're looking at, and then I'll prove it algebraically. Now, if they said pi over 2, what units do you think they're assuming here? Yeah. They're in radians. I'm in degrees, so I need to switch to radians. And let's see what it looks like. So there's what's on the left. There's what's on the right. So they look the same. And they are. So now we're gonna try to prove it. When you want to verify an identity, which side do you always start with? Yeah?
More complicated side.
Always start with the more complicated side and try to simplify it. So we're going to start with that. And we're going to use the formula for cosine difference. That's my first angle. That's my second. So instead of 45 and 30, now you've got pi over 2 and theta. So one of them's a number, one of them isn't. Right, so Ashley, when I write the cosine difference formula, what do I start out with?
What do you mean?
So when I want to kind of expand this out using the cosine difference identity, just like we did cosine 15.
So you do cosine of pi over 2.
Yep. So cosine first. Yep.
And then cosine of the second number.
Cosine second. So we've got cosine first, cosine second. So that's the first part.
And then plus
Yep.
sine of the first one.
Sine first. Yep.
And then you don't have the second.
And I'm just going to fill in sine second. Okay. Now we're going to do out whatever we can, and we hope that when we simplify the left-hand side, somehow we just end up with sine. Okay, let's start with the cosine of pi over 2. That's like 90. What's the cosine of pi over 2 or cosine of 90? Yeah? That would be the sine of 90. So that's actually going to come up over here. Think of the graph of cosine. Think about where it is at pi over 2. That's 1/4 of the way through the cycle. Remember, anyone have a guess? Cosine? I mean, it's not like a crazy decimal. It's one it's an easy number. That's the only reason I'm asking, and I'm not using a calculator.
0.
It's 0. Okay. If you draw a cosine out, remember, it starts up here, comes down, and it looks like that. The start, quarter, half, 3/4, full cycle. So the question is pi over 2. That's 1/4 of the way through the cycle. You're at 0. Right. So cosine of pi over 2 is 0. Now you can't really do much with the cosine theta, and you can't really do anything with the sine theta. Those just kind of stay. But what's 0 times cosine theta? 0. This whole part's gone. It just canceled out. And then what's 1 times sine theta? Sine theta. So by filling in, using our cosine difference identity, the one that I gave you at the beginning, and filling in those two angles, we ended up with sine theta, and that's what we wanted to prove, that it's sine theta. And so what this is basically proving is that cosine is basically a horizontal shift of sine. It's a 90-degree shift, or a pi over 2 radian shift. And this identity, that proves it. Okay, so any questions on that? So there's two very similar to that on the test. Okay? It could be a sum here or a difference. It could be a cosine here or a sine. We haven't learned sine yet, but it's very similar to what we're doing right now. All right, we can try this one. It's another one that's on the same idea. It's a cosine. It's a difference. So I'm trying to remember my formula for the difference of a cosine. This gets a little harder because then you're going to have 4 formulas eventually. Cosine of a difference, cosine of a sum, sine of a difference, sine of a sum. All right, so Robin, if I want to start with the left-hand side and plug into my cosine difference identity, what's the first thing I would write?
Cosine of pi.
Yep.
Times the cosine of theta.
Yep. So you've got cosine, cosine.
Plus.
And the thing you want to kind of remember here, which I've never pointed out, is the sign that you put here is the opposite of the one you have there. So when we do a sum, you can probably guess what's going to happen. So that's good. So plus
the sine of pi over, or not over, times the sine of theta.
Okay. So cosine pi and sine pi are the only two things we can figure out. So let's think of the cosine of pi. Pi is halfway through the cycle. Where are we at halfway through the cycle? Yeah?
-1.
-1. So -1 times cosine plus, now sine, you want to think of a little different graph. Start, quarter, halfway, 3/4, all the way. So now I want the sine of pi. What's that? 0. So 0 times sine. So if this was on a test, I'd be looking first that you did this. Show me you plugged it into the cosine difference formula. Then you evaluated the two things that you could. Usually one of them cancels out, and all you're left with is negative times cosine.
So negative cosine.
Which is just negative cosine. So even though verifying trig identities can be hard, these are kind of simple because you already know the same formula to plug into every time. And 2 of the calculations come out. 2 of them you can do and 2 of them you can't. And the ones you can do either come out to 1s, 0s, and -1s pretty much every time for this kind of problem. Questions on that? All right. So let's see if we can figure out the cosine sum formula. And we know the cosine difference. So it's not really that hard to get the sum. Okay, there's two things we have to remember, and we did these a while ago. So just a couple reminders that if you take the cosine of a negative angle, the negative doesn't matter. You can try it. Take the cosine of negative 12. Take the cosine of positive 12. You're going to get the same answer. Now that's with cosine. With sine, the negative does matter. But what you can do is you can put the negative in front. So like if you wanted the sine of negative 12, that's the same as the negative sine of 12. Right? So these two ideas we've mentioned before, but we need them right now. These are what you call even-odd identities. Okay, I never called them that, but that's what they are. They're called even-odd identities. You don't need to know that. So here's cosine of a sum. Let's focus on alpha plus beta. Okay, for a minute. How can I rewrite that using subtraction? Because if we can write it with a subtraction sign between alpha plus beta, then we can do it. But we just have to write something that's equivalent to what we have now. Think how you can write. How can you write a sum, and it could be even numbers? How could you write a sum of two numbers as a difference? Let's pretend that your plus button was broken on the calculator and all you got is a minus button. You can still do addition. You're just going to have to press more buttons to do it. Yeah? Minus the negative. Right? So we're going to think of it this way. Alpha minus negative beta. And the reason we want to think of it that way is because we have a formula for when that sign is a difference. So if we use the formula we already know, we can figure out the formula for a sum. Now, technically, you don't need the formula for a sum. You could do every sum problem as a difference problem with the formula I already gave you, and never use the one that I'm about to show you. But if you can remember this one, it's quicker than doing a double negative every time. That takes longer. Right, so let's set this up. So think of it as, here's your first angle, here's your second. So the first angle is alpha, the second angle, negative beta. Right, so Gabe, if I want to write this out, just like we did in the last two, what's the first thing I write down when I do my difference identity?
Cosine.
Yep.
Alpha.
Yep. So cosine of the first times
Cosine.
negative beta. So cosine, cosine. What comes after the cosines? Plus or a minus? Well, Nate, what comes after those cosines?
I think it's, yeah, I don't know.
Yeah. Let's go back and check. Plus. So whenever we're doing a difference formula, we always put a plus. And that's what we're doing right now. We're doing alpha minus negative beta. Right? So it's a plus. And Kathleen, what comes after the plus? Sine. Yep, alpha. And sine negative beta. Now, let's use these two ideas and simplify what we have down there so we don't have negatives inside the angles. What can I do with this negative on the beta when inside the cosine function? Yeah? And just get rid of it. It doesn't make a difference. So cosine alpha, cosine beta. Now, what can I do with this negative on the beta in the sine function? Can't get rid of it. Yeah?
Move it to the front.
I can move it to the front. So I can do minus sine alpha, sine beta. So what's the difference between the cosine sum identity, which now you have right here, and the cosine difference identity? It's only one thing that's different.
There's a subtraction.
Yeah. The sum identity has a subtraction sign. The difference identity has a sum. Okay? But they're both cosine, cosine, sine, sine. One has a plus between them, one has a minus. So now that I know, again, the cosine sum, what angle do you think I could figure out the cosine of? Kind of like we did 15, because we did a difference of two numbers. Now I'm going to do a sum of two numbers. What angle do you think I could do that we haven't done before? Well, think of an angle in the first quadrant that you can get by combining 30s and 45s. There's other quadrants, but we're going to stick in the first quadrant for now.
75.
Right, so now we can do 75. Now, you could have done 75 before, if you could think of a way to write 75 as a difference. But when I think of 75, my mind naturally goes to writing it as a sum. I think that's easier. So how can you write 75 as a sum of angles that are multiples of 30 and 45? Bless you. How about Jared?
I'm not sure.
Not sure. Do you know what I'm asking?
Not really.
So I'm asking how to write 75 as a sum of two numbers. And the two numbers have to be multiples of 30 and 45.
So do 30 and 45.
Yeah, just 30 plus 45. Now, that's how I'm going to do this problem. Let's pretend somebody doesn't know the sum identity. All they remember is the difference. I told you, you don't need the sum. How can you write 75 as a difference of two numbers instead? Something minus something. And you get 75. I mean, it can't be like 85 minus 10. It's got to be two numbers you can subtract. And the numbers have to be multiples of 30 and 45. Yeah. Did you have a guess, please? No. Yeah?
Minus
All right, so what are you thinking? You're thinking what minus what?
You could do 30 minus negative 40.
Okay, yep, you could do it that way, which technically satisfies my question. Perfect. You could just do 30 minus, which is kind of the same thing. You could even do it with other numbers than 30 and 45. Yeah?
Could you do 90 and 15? Wait.
We want to try to stick with numbers that are multiples of 30 and 45. Anyone think of another way besides 30 minus negative 45? Yeah?
120 minus 45.
Yes. You could do the cosine of 120 minus 45. Because 120 is a multiple of 30, 45 is a multiple of 45, and you could do this exact same problem as a sum, as a difference, if you didn't want to do it as a sum. Right? But let's try it as a sum, okay? Because that's what we're going to do. So we're going to use this. These are just other options. Most of the time, I'm not going to tell you how to do it. I'll just give you the problem. You can figure it out however you want, sum or difference. All right, so if we're going to do this as a sum, we've got cosine, cosine, sine, sine. And I know it's first, second, first, second. What goes between them if you're doing the first one? Yep. What go? So when we have a plus minus, right? So it's always with cosine, it's the opposite. All right. It's going to get a little more confusing because with sine, it isn't. When you have sine of a sum, the formula has a sum. Sine of a difference has a difference. But cosine, it's the opposite. All right. So sum, we write it as a difference. 30, 45, 30, 45. Right, so let's go through. And some of these values we already have. We need to change back to degrees though. All right, so Jacob, what's the cosine of 30 as an exact answer?
The cosine. What do you mean by exact answer?
Well, I can see it's 0.866, but from the first problem we did, what's 0.866 as a fraction?
As a fraction, it's 866 over 1,000, or 433 over 500.
Well, you got to have all the decimals. You can't round it to 0.866.
No, I'm not sure how to do that.
Anyone remember what that one is? It's got square roots in it?
Square root of 3 over 2.
Yes. Square root of 3 over 2. Cosine 45, we did that one earlier. What was the cosine of 45? Yeah.
Square root of 2 over 2.
Yep. If you know these, it's very, very quick. Sine of 30. I think we did that one earlier. Yep, that's a half. And the sine of 45, it's the same as the cosine of 45. 2 over 2. All right, so I'm going to do this as a final answer. What's my denominator going to be? It's going to be 4. It's going to be minus. In my numerator, what's my first term?
Yeah, root 6.
Root 6. Second term? Yeah.
Root 2.
Root 2. So you see root 6 and root 2 a lot in these problems. Sometimes it's plus root 6 plus root 2. Sometimes it's minus root 2. Okay? But you're going to see root 6 a lot because you're dealing with root 3s and root 2s. Okay. Any question on that one? Okay, so again, sine and cosine formula, kind of redundant because sine, cosine sum, cosine difference, because you can use one or the other. You never need really both. All right. So let's see if we can figure out the sine of a sum. Now, even this formula, you don't need it. Since we know that we proved this earlier, I graphed it on the calculator. You really, if you had a sine problem, you could use this identity and rewrite it as a cosine problem. But it is faster if you don't have to rewrite it every time, kind of like using that double negative to mean addition. That's going to slow you down a little bit. So if you just know the actual formula, it's easier. Alright, so let's see if we can figure this one out. Just use what's right here. Alright, so it says that if you want to take the sine of an angle, it's the same as the cosine of pi over 2 minus the angle. So here's the angle. It's alpha plus beta. So how could I write that using the identity I have right up above it? So in our problem, instead of this, you have this. Just think of it as that. The sine of box is equal to the cosine of pi over 2 minus box. Just fill in whatever's in the box. If it's a theta, fill in a theta. If it's a what I have there, fill in what I have there. Yep.
Would be pi over 2 minus alpha.
Yes, pi over 2 minus my angle. Now what I'm going to do with that negative is I'm going to distribute it. Okay, so I'm going to do minus alpha minus beta. All right, so let's do that. So cosine pi over 2 minus alpha minus beta. Okay, now what I'm going to do is I'm going to regroup it because I've got kind of three things there. I really want to write this as, I want to write it like this. Cosine of something minus something. Okay. Right now it's not really set up like that. So let's group it like this. Cosine of, let's do pi over 2 minus alpha. And let's just kind of put the minus beta separate. So now I have something minus something. And what I've just done is a cosine difference. Here's my first, here's my second. So go back to the cosine difference formula, it's the first one we did, and fill in that for your first angle, that for your second. And there's other ways I could have grouped it to split it. It's just this, they're all going to lead to the same answer. But hopefully this one will be the easiest. So it's cosine, cosine, sine, sine. First, second, first, second. So first, second. First and second. And what goes between them? When you have a cosine difference, you put a what between them? Yep,
Plus.
a plus. Now, let's go through and see what we got. Look at this first one. Cosine of pi over 2 minus alpha. Cosine of pi over 2 minus box. What's the cosine of pi over 2 minus alpha the same as? Yeah. The sine of alpha. That's why I did it that way. Cosine of pi over 2 minus alpha is the same as sine alpha. So now you have sine alpha, cosine beta, and now this part right here, sine of pi over 2 minus alpha, it's kind of like this identity. We didn't write it, we didn't go through the proof on this one. But what do you think the sine of pi over 2 minus something is? If it kind of follows the same pattern as what's up above. Now, it's the same as, yeah, it's the same as the cosine. So you have this, if you have the sine of pi over 2 minus something, it's the cosine. If you have the cosine of pi over 2 minus something, it's the sine. So let's go back down. Sine of pi over 2 minus something. Yep, sine of pi over 2 minus something, that's just the cosine of the something. And then the sine beta is left right where it is. So that's your formula for the sine of a sum. It's sine cosine plus cosine sine. A couple things that are different. It's the sine of a sum. The answer has a sum in it. Also, the sines and cosines aren't together. It's sine, cosine, cosine, sine. First, second, second. You might see it written differently, like you could do cosine beta sine alpha, 2 times 3, 3 times 2, same thing. Okay, but that's the sign of a sum. One thing changes there to get the sign of a difference. Anyone think they know what I would change here to make that formula into a difference? Yeah?
The that plus sign would change into a minus sign.
Yeah. So it's still sine, cosine, cosine, sine. First, second, second. Except now it's a minus. Okay, so when you deal with the cosine identities, cosine, cosine, sine, sine together. When you deal with the sine identities, it's one of each. Sine, cosine, cosine, sine. But the way that I wrote them, it's always first, second, second. First, second, second. Okay. Even back to the original formulas I had at the beginning of class. First, second, second. That's why I put them in that order. So I always just remember first, second, each for everything. Cosine identities, the sign is the opposite. Sine identities, it's the same. Minus, minus. Okay. So I'm not going to go through, but you could do the same problems we did with cosine. I could ask you what's the sine of 15, right? And you would do it as like the sine of 45 minus 30. Or if you want to do it a different way, you could. Same thing with sine 75. Sine 30 plus 45. So any questions on how you would use these two formulas to do something like that if it said sine 75? All right. Now, what's the formula for tangent? When we did trig identities, tangent was the same as what over what? Yeah.
Sine over cosine.
It's sine over cosine. So, if you had to do a problem like this, I would hope at this point people could do that. All you'd have to do is do the sine of 15, then do the cosine of 15, and divide them. That's not the fastest way to do it, but it would work, right? If you want a faster way to do it, there is a tangent sum identity. I honestly never remember what that is, because I don't do enough tangents to make this formula worth me memorizing. I would just do the sine over the cosine every time. If I had to do a lot with tangents, like every day, then it would be faster to learn this formula because it does everything in one step rather than using 2 steps. And the difference between the plus and the minus, it's just changing the signs, just like every other formula. Okay, so in the top, it's always tangent, and then if it's a sum identity, you use sum. If it's a difference, you use difference on the top. But then it gets kind of weird because in the bottom, you use the opposite sign. So whatever you used in the top, if you use plus in the top, you use minus in the bottom. If you use minus in the top, you use plus in the bottom. Right, so I think at this point then it's starting to get a little hard to remember everything. Okay. The sines and cosines one, those you need to know. But if there was ever a question with these, I would probably give you this formula. Unless I said just try doing it with the sine and cosine formulas, like I showed you right here. Okay, but that's not something you'll need to memorize. But I would use it in the homework because you can look it up and it is faster. Okay, so there's your sum and difference for tangent. Alright, so let's look at this. So a little different. What we're looking at now is a product, okay, inside, 2 times x. Well, taking the 2 and just throwing it in front is not the same thing. Even from a transformation perspective, that's a vertical stretch by a factor of 2. That's a horizontal compression by a factor of 2. They're not even the same transformation. So, let's figure out what sine 2x is then. If it's not 2 sine x, it must be something else. So we're going to figure out what the sine 2x one is. That one's pretty easy. There is one for cosine 2x and tangent 2x. We're not going to figure them out from scratch. Alright, so let's look at this. This is example 4. I'm not going to do it as a verify. I'm just going to give that to you. And you can leave the word verify here. And I'll fill in what it's supposed to be after, but I don't want you to see it before we actually do the problem. So I'll finish writing this in at the end. And that's what we're going to get, what's inside that box. What's another way to think of sine 2x besides a 2? Like, think about how would you get 2x in an algebra problem if you did what? Besides times. Is there any other way you could get 2x as an answer if you did some algebra? Yeah. You added 2 x's together. And look what you have right there. That's a sine sum identity. When we have a sine sum, is the symbol that I put down here the same or the opposite of what's up there? Oh, Joe? Is the symbol the same or the opposite? It's the same. Yep, for the sine identities, it's the same. Now, is it cosine, cosine, sine, sine? Or do I use one of each in the sine identity?
One of each.
Yep. I use one of each. So that's what we had, right? Here. Sine, cosine, cosine, sine. Okay, so sine, cosine, cosine, sine. And all my arguments, they're all x. So I have a sine times cosine plus a sine times cosine. What would that be if I combine it together? Gabe. Sine times cosine plus cosine times sine. It's kind of like x times y plus y times x. What would that be if you put them together?
Would just be
I don't think they could tell me. Well, what's y times x the same as? It's the same as x times y, okay? What's xy plus xy? Yeah? Yep, 2xy. So what's sine cosine plus cosine sine? Yeah? Exactly. 2 sine cosine. So the sine of 2x.
Wouldn't it be 2 cosine x?
Yes, thank you. No plus sign there. So the sine of 2x is the same as 2 sine cosine. And that's what it was going to say right here. Or if you use theta, it's theta, but whatever the letter is. So that's a double angle identity. What the double angle identity does for you is it takes where you had a 2 next to your angle, and it gets rid of it. Now you just have your angle, and you just have your angle, and you end up with a 2 in the front. For cosine, little different identity. Okay, this is usually one I have to look up. I can remember this one, that the sine of 2 theta is 2 sine cosine. This one, sometimes I get mixed up with the Pythagorean identity, which is sine squared plus cosine squared. That's different. And the cosine one, you can actually write different ways. You can write it as cosine squared minus sine squared. Or, if you use this identity, which is totally separate, that's a Pythagorean identity, it has nothing to do with this right now. But if you substitute in for sine squared, like doing something like this, like you can get sine or cosine squared either way, if you substitute in, that's where this 1 minus stuff is coming from, right? You can substitute in for cosine squared and get that, or you can substitute in for sine squared and get that. Because if I filled in cosine squared with 1 minus sine squared, I'd have 1 minus sine squared minus sine squared. So you subtracted sine squared twice. That's where that 2 comes from. Which one of these 3 formulas you use? You can use any of them. It kind of depends on the problem, whatever's easiest. And the double angle formula for tangent. I would say out of those 3, the 2 most important ones are the sine 2 theta equaling 2 sine cosine, and the cosine 2 theta. Off the top of my head, I don't know all 3 of those. I only remember the first one. Because if I remember that one, I can figure out the other ones. Right? There's already too many identities to try to remember. So out of this page, that and that are the 2 most important things to remember. And if you asked me to do tangent of a double angle, I would probably just do the sine over the cosine, because I don't have the tangent one memorized at all. Right, so what that does is now it gives you, it just gives you ways to calculate something like let's say you had to figure out the cosine of, I don't know, 90. And for some reason, you couldn't remember the cosine of 90, but you could remember the cosine of 45. Well, that'll work. Because you can think of 90 as 2 times 45. There's your first, there's your second. And now you could just fill in those 2 angles. I mean, you should know the cosine of 90, but if you didn't, you could figure it out as long as you knew 45. So these formulas just give you kind of different ways to figure things out if you don't know certain pieces of information. Kind of work around what you don't know. All right, so let's take this, and the kind of problem you're going to see with this is rewrite it so you don't have any numbers in the argument. All you're allowed to have is x's. Well, this part's fine. You can have a number in front, but they just don't want numbers other than 1 next to the x's. So how can I rewrite sine 2x so that there's not a 2 in front of the x? Yep. Okay, and then the sine of x plus x, what did we just figure out that that is? We had a double angle identity for that. Yep. 2 sine cosine. 2 sine cosine. And technically here I'm done. I've done what they wanted. if it was a matching question and you didn't see that listed as an answer, you might see something like this. How did I get that? What did I do? Anyone see what I did to get from that to that? It's kind of like if I had 2x plus 2 yx. And I wrote that as 2x times 1 plus y. What did I do here? And it's the same thing I did up here.
Just like distributed.
I did the reverse of distributing it, which is factoring. All I did was factor out what it had in common. The directions didn't say to do that. I just showed it to you in case you get this on a test and it's a multiple choice question and you see that. It's the same thing. You just factored out the GCF. All right, there's that one. All right, let's, all I want to do with this one is I'm not actually going to solve it. I just want to rewrite it so that it's x's. Just x's. And then I'll finish up, I'll give you the half angle formulas. But again, I'm giving them to you because you might see them in calculus. We're not going to really do a lot with them. But it gives you, the half angle formulas give you more way to get around things if you don't know something. It just gives you more options. It's like, okay, I don't know that, but I know this. So you can kind of figure other things out. All right. Let's start with sine 2x. Okay, again, we're not going to solve for zeros. Just rewrite in terms of sine and cosine. Okay, what's sine 2x? Let's deal with that first. Yep. 2 sine cosine. That part's done. Now, what's kind of hard about that second part? Yeah?
Well, we only have equations of cosine 2.
Right. That's a triple angle. We don't have triple angle formulas. We have double angle formulas. So somehow we have to use the double angle formulas to figure that out. I mean, you could write formulas for every single angle. Quadruple angle, 5x, 6x, 7x, but it's just way too many formulas to remember. So we got to stick with the ones we know. The way we're going to do it is think of 3x a different way. How could you do algebra and get 3x as a final answer? What could have been a calculation that led to 3x? Yeah?
X plus x plus x.
X plus x plus x, or I'm going to just do it in two parts. I'm going to think of it as 2x plus x. Now, what do I have right there? What kind of thing is in that box? Yeah, that's a cosine sum. So now you've, instead of a 3x, now you've written it as 2x and x. Now use your cosine sum identity, which will separate that out. You're still going to have some 2x's, but that's fine. We have formulas for 2x's. We just don't have formulas for 3x's. So let's leave this part the same. And now cosine of a sum. Is that where I do cosine, cosine, sine, sine, or one of each? Yep.
What do you mean?
Oh,
Cosine?
let's go back. Cosine of a sum. That was sine of a sum. Cosine of a sum. Cosine, cosine, sine, sine. So they're together with a minus between them. All All right, so we've got, where are we? So we've got cosine, minus sine, sine. Remember, first, second, 2x first, x is my second. So 2x, x, 2x, x. Okay. Usually when you take something and you're trying to get rid of a 2 or a 3 in front of the x inside the argument, it gets messy. It's not easy to get rid of a 2. Or if this was like a 4 or a 5, this would be like 30 to 40 terms long. It gets really long. A 3 is not too bad because there's only 2 more things we have to get rid of and then we're done. Everything else there is fine. So the 2 sine cosine is fine. Now the cosine 2x, we can't leave that, but we've got several choices. Since I just said to rewrite as sine and cosine, you can pick any version of the cosine 2x formula. So what's one version that we could use? Yep.
Cosine squared minus sine squared.
Cosine squared. Okay, just go back so we can see it. Cosine squared minus sine squared. It's the very first one. So cosine squared minus sine squared. So now we only have a 1 in front of the x, 1 in front of the x, 1 in front of the x, 1 in front of the x. Keep parentheses around that because that cosine x is right next to it and it's still multiplied. It's just now you have a difference inside. Minus. One last thing we have to fix. What's sine 2x? Yep.
2 sine cosine.
2 sine cosine. 2 sine cosine. Now, I have another sine at the end. How can I combine it with what I have right there? Mainly because I'm out of space. I have 2 sine cosine sine. Yep.
2 sine squared.
Yeah. It's minus 2 sine squared because you get a sine from here and from there. And now, every single thing inside the parentheses, they're all x's. There's no 2's. There's no 3's anymore. And you could distribute out that cosine, like you can make it cosine cubed minus, you might even be able to combine like terms, minus sine squared cosine, minus sine squared cosine, but that's good for that one. All right, and you wouldn't see anything higher than a 3, because it gets pretty bad when it gets higher. Okay. Any questions on that? So the last one, these are your half-angle formulas. Again, half-angle formulas, I don't have any of these memorized off the top of my head. Okay? I just don't use them enough to remember them. If I needed it, I would look it up. But honestly, anything that would require me to use the half-angle formula, I can probably figure out a different way to do it without using this formula. So let's say, I don't know, you had to figure out the sine of 150. And for some reason, you just couldn't remember the sine of 150. Well, actually, no, let's do it this way. This would be easier. You had to figure out the sine of 75. Yeah, half. If you had to figure out the sine 75, I showed you guys one way to do it. But another way to do it is to think of it like this. Maybe for you, it's easier to think of it as 150 divided by 2. Instead of if you don't remember the sine sum identity, you could use this formula, and it would work. Okay, so it's really all just different ways of kind of doing the same thing. So you've got cosine theta over 2, sine theta over 2, and tangent theta over 2. And each time you're starting with something divided by 2. And you're ending up with just the something and the something. There's no divided by 2 in the theta anymore. And those are called half-angle identities. Out of all the ones we did, definitely not the most important ones for us. Any questions on these? All right, so homework due probably tomorrow, as long as we have class. If we don't, next time we have class. That's 1 through 5, 9 through 11. That's all, and then it just skips around. 17, 18, 29. 31, I think, has multiple parts, just do part A. And then 37, 41, and 45. Okay, so we'll take a look at that next time we have class.